Hi everyone. In this video we're going to go over the nth term test to determine if a series diverges. Now we're first of all going to cover this theorem. Now this is actually the nth term test here, but it's not the version that we're going to use. So the theorem here makes this statement. If we have a series that converges, then the limit as n goes to infinity of the an terms must equal 0. That should intuitively make sense because if you're adding up terms, a1 plus a2, all the way to infinity, it seems reasonable that for this number to exist, these numbers, the individual numbers in your sequence, must be getting closer and closer and closer to 0. If they aren't, then it seems like this series should diverge. And that's actually what the nth term test states. So that's the statement of this theorem. If you have a series that converges, then the limit of your an terms as n goes to infinity must equal 0. Now let's take a look at the proof of this theorem, and then we'll consider the contrapositive of this theorem, which is actually what we call the nth term test. Now the statement of the theorem is that if the series converges, then the limit of the an terms is 0. So we will assume that the series converges. So we're going to assume this. We must prove that this holds. So if we assume the series converges, that means that the summation of your an terms is equal to some number L that exists. Okay, we must prove the limit of the an terms is 0. Now what does it mean to say that the summation converges or that this holds? Well, it means that the limit as n goes to infinity of your nth partial sums is equal to this number L. Remember that? That's what we define convergence to mean. Now the nth partial sum is the sum from 0 to n of your ak terms. Remember, this is just a0 plus a1 plus a2 out to an. That's the nth partial sum. And it doesn't matter whether you start at 0 or 1, it just depends on your series where you're starting. Then convergence means that the limit as n goes to infinity of the s sub n sequence is equal to L. Now what we're going to do is consider the nth partial sum and the n minus first partial sum. Okay, so the nth partial sum is this, right? We sum from a0 out to an. The n minus first partial sum is you sum from a0 to an minus 1. Now if you consider the difference between those two quantities, so you subtract s sub n minus 1 from Sn, notice that you'll get cancellation with everything except this last an term, right? If we take this minus this, all of these a's will cancel out to the an minus 1 term because of that term right here, and we'll be left with this. So Sn minus Sn minus 1 is equal to a sub n. So therefore what we have is this. The limit as n goes to infinity of a sub n is the limit as n goes to infinity of s sub n minus s sub n minus 1. And by properties of limits, we can distribute this lim to the Sn and to the s sub n minus 1, like we do right here. However, both of these limits right here, this limit and this limit, are both supposed to be L because they're supposed to exist and equal this number up here, right? Now notice this one is s sub n minus 1. Well, it doesn't really matter. This limit is still going to equal L, right? As n gets very, very large, as little n gets very, very large, this quantity is approaching L, right? So as n gets very, very large, so does n minus 1 get very, very large. So this quantity is also approaching L, right? So you see what we have then is both of these limits are equal to L. So you get L minus L, well, that's 0. So we've just proven that the limit as n goes to infinity of an is equal to 0. There you go. And our proof is complete. Now let's take a look at this. We're actually going to do just a little bit of logic in this course. So the contrapositive of an if-then statement, like if A is true, then B is true. The contrapositive of that statement is if B is not true, then A is not true. Okay, so for example, think about this statement. I make the statement, if I am washing my car, then it is sunny outside. Okay, the contrapositive of that statement is to say, if it is not sunny outside, then I am not washing my car, right? So once again, let's just notice here with this statement, A is the statement washing my car, and B is the statement that it is sunny outside, right? So this is the statement, if A, then B. If I am washing my car, then it is sunny outside. All right, so this is your A statement, and this is your B statement. Okay? Now, the contrapositive of that is to say that if it is not sunny outside, so you see that's B is not true, then I am not washing my car. So A is not true. So that's the contrapositive. Okay, now if you think about this for a little bit, those two statements say the same thing. Just think about that for a second. To say, if you see me washing my car, it will be sunny outside. Now think about the statement, if it's not sunny outside, you will not see me washing my car. Those statements say the same thing. So we actually have this result down here that says the contrapositive of an if-then statement is actually the same as the original statement. They are equivalent statements in truth value. Okay, now this is a statement that you would prove in a logic course or in a mathematical proof techniques course. So we're not going to go over the details of this, but if you think about it for a second, like with this example up here, it should seem reasonable that a statement and its contrapositive are equivalent statements. Okay, now let's think about the previous theorem that we looked at. It made the statement that if your series converges, then the limit as n goes to infinity of the an's is equal to 0. Okay, so this is your A, and this is your B. Okay, if A, then B. Well, the contrapositive of this statement is to say that if the limit does not equal 0, then the series does not converge, or that it diverges, right? That's the contrapositive of this. And this theorem tells us that they are exactly the same. So therefore, from our previous theorem, we have what is called the nth term test, and it makes this statement. If the limit as n goes to infinity of an does not equal 0, then the series involving the an's diverges. So that's the nth term test. It's merely the contrapositive of the previous theorem that we looked at. Now let's see how we use this theorem. This comes in handy. Let's take a look at this example. So let's determine if this series, the sum of n over n plus 1, converges or diverges. Well, let's note that for this series, our an terms are equal to n over n plus 1. And let's also note that the limit as n goes to infinity of n over n plus 1, well, that's equal to 1, right? Which does not equal 0. So therefore, the series involving these terms diverges by the nth term test right here. And that's all you have to do. That's pretty simple. Now, it is important to note one thing here. If the limit of your ANs does equal 0, the nth term test is not telling you that the series converges. Do not make that mistake. That's what we're pointing out in this note down here. So let's take a look at that in good detail. So please take note of this. The nth term test does not make the statement that if the limit is equal to 0, then the series converges. This is absolutely not true, okay? So do not think that it is telling you that. For example, if you consider the limit as n goes to infinity of the sequence 1 over n, of course that is equal to 0. And yet, if you look at the sum from 0, well, actually that should be from 1 to infinity, of 1 over n, that's going to be 1 plus 1/2 plus 1/3 plus 1/4 and so on, that actually diverges. And we will prove that later on, okay? That's easy to prove with what's called the integral test. So even though your limit of this series, even though the limit as n goes to infinity of 1 over n does equal 0, that is absolutely true, this series, as we'll see later on, diverges. Okay, that actually diverges. So don't make that mistake. Just because the limit of your an terms is equal to 0 does not mean automatically that your series will converge. It might converge, but it doesn't guarantee it will converge. Okay, let's take a look at a few more examples now. Now here's a definition that we need. For any non-negative integer n, we define this little n with an exclamation mark after it. That means n factorial. Now that's supposed to be the number 1 times 2 times 3 times all the way out to times n. Now also, if n does equal 0, then we define 0 factorial to be 1. That may seem a little counterintuitive. You would probably guess that 0 factorial should be 0, but no, we define 0 factorial to be 1, and there's good reason for that. If you study higher level mathematics, this makes the factorial a little more consistent. For example, what would 5 factorial equal? Well, 5 factorial is just going to be 1 times 2 times 3 times 4 times 5, or 120. That's all you have to do. Let's take a look at this one. What is n factorial divided by n minus 2 factorial? Well, considering what we have written down here, you see n factorial is going to be 1 times 2 times 3 times all the way out to, and we write out a few terms at the end, n minus 2 times n minus 1 times n. Now n minus 2 factorial is 1 times 2 times 3 all the way out to times n minus 2. So you notice how these cancel right here. These cancel. And you're left with n minus 1 times n, or n squared minus n. So there you go. That's what n factorial divided by n minus 2 factorial is equal to. Now another way to see that is to note that you could write n factorial as n minus 2 factorial times n minus 1 times the next term times n, right? And then n minus 2 factorial in the denominator is right here. Of course, these cancel, and you get n minus 1 times n. There you go. Okay, let's take a look at this example now. So let's determine if this series converges or diverges. So the summation from 1 to infinity of n to the nth power divided by n factorial. All right, well, let's consider the an terms, which are n to the nth power over n factorial. Now, n to the nth power is going to be n times n times n dot 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 times n, and this will be n times. So you have n of these numbers n, whatever they are. You know, for example, 4 to the 4th power, that's 4 times 4 times 4 times 4. So you got 4 4s being multiplied. Okay. Then in the denominator, you have n factorial. So that's 1 times 2 times 3 all the way out to n. Now let's break this fraction here apart a little bit. Write it as n over 1 times n over 2 times n over 3 all the way out to times n over n. So that's what we have right here. Now you'll notice that this is always going to be bigger than n, right? Now you see that because right here is n. That term right there is n, of course. And all of these numbers are bigger than or equal to 1, and they're all being multiplied against each other. So if you take a bunch of numbers and they're all bigger than or equal to 1, and you multiply them against each other, you're going to get a number bigger than or equal to 1. So of course this quantity is bigger than n. Okay, so therefore what we have now is this. Well, let's look at the limit as n goes to infinity of these terms. So we see now that the limit as n goes to infinity of n to the nth power over n factorial, well, since each of these are bigger than n, this limit is going to be infinity, which does not equal 0, of course. That does not equal 0. So by the nth term test, our series must diverge. And there you go. So we have now determined that this series actually diverges. That should make sense, you know, immediately after we did this analysis right here. Because you see what you're doing when you're adding up these terms. Each of these terms is going to be bigger than n, so you're adding up numbers that are even bigger than 1, 2, 3, 4, 5. So, of course, when you add them up, you're diverging to infinity. And that concludes this discussion about the nth term test.